In this video, we're going to look at finding the length of a line segment, or if you like, the distance between 2 points. All we're going to do is use Pythagoras Theorem to find the length of the hypotenuse of a right angle triangle. Let's start off with a basic example. What I'm going to do is plot a point, and that first point is going to be just here. I'm going to call this point A, and A has the coordinates 2, 1. If I plot another point, I'll call that B. I'm going to put that at 6, 4. So we'll have B, which will be 6, 4. What I might be asked to do is find the distance between these 2 points, or the line segment AB. So we might be asked to find the length of this line segment. This is a nice straightforward example, and all I'm going to do is create a right angle triangle. So if I come across from A and then go up to B, I have 2 perpendicular lines. So these are at 90-degree right angles. If I go ahead and put a right angle here, we've got 2 shorter sides and a hypotenuse. Pythagoras Theorem says that a squared plus b squared is equal to c squared. So if we square each of the shorter sides and add them together, that will give us now the value of the hypotenuse, or the longer side, squared. So let's go ahead and count these squares. We've got 4 going across, and we've got 3 going up. Using Pythagoras Theorem, I can simply say now that this length squared, which I'm going to call AB squared, is going to be equal to A squared, which is going to be 4 squared, plus b squared, which is going to be 3 squared. It doesn't matter which you call A and which you call B. So that's going to give us now that AB squared, so the hypotenuse squared, and of course you can call that C, that's going to simply be 16 plus 9. That's going to give us that AB squared is equal to 25. We take the square root and we need the positive value, so we can say now that AB is going to be equal to the square root of 25, and AB will be equal to 5 units. So all I've done is found the length AB using Pythagoras Theorem. Clearly we don't always need to show this amount of work in, but I've just done it right the way through just to show how it's done. This was a nice example because this was one of our 3, 4, 5 triangles. It won't always be that pretty, and that's where we use what we call the distance formula. So let's have a look at another example. What I'm going to do is put a point just here. Let's go for one just here. And then I'm going to put one just, where else should we go? We'll go just there. That looks good. So we'll have 1 point just here. So let's call this one P. So P has the coordinates -5, +3, and we'll call this one down here Q. And we can say now that on this one, Q has 3, -3. Again, what I could do here is draw a line between them. We would call that line PQ, and that is a line segment. This again is a straightforward example. We can make a right angle triangle, so dropping a line down and a line perpendicular, so at 90-degree right angles, across. If we consider now the right angles here, what I've got is a base. This base is going to give me now 8 units. So if we look at that, that's 8. The height here is going to give me 6, so I could say my base is 6 and my height is 8. And we can see that the length of the line segment PQ is going to be 10. 2 different ways to think about that. We can see that it's double the previous triangle, so if AB was 5, PQ is going to be 10. Or of course we could use Pythagoras Theorem and say that PQ squared is going to be equal to 8 squared plus 6 squared. That's going to give us 64 plus 36, which is going to give us 100. Therefore, and using the therefore symbol, those 3 little dots, we can say now that PQ is going to be the positive square root, and it's a positive square root as it's a length. We can't have a negative length. That is just going to give me 10. Okay, so nice and straightforward. It really is. Let's look though, if we had, for example, a point, and I'll just put a point on, and we had a point just here, and it was this point right here. So this point, let's call this now r. We'll have r just here, and we'll say that the coordinates of r are going to be 3.5, negative 1.5. And then if I put another point just here, and I'll put this one just here, this point here, this is going to be s, and s is going to have the coordinates 0.75, negative 3.75. Quite clearly, drawing a line between these and counting the squares across, as we've done before, is not going to be an easy way to do this. So what we would do in this particular case is use what we call the distance formula. The distance formula is very straightforward. What we say is that d squared, which is the distance squared, and I'll just write it here, d squared is equal to x2 minus x1 all squared plus y2 minus y1 all squared. Don't panic when you see this. This is really quite straightforward. What I'm going to do is just apply it here and show you how straightforward this is. So if we consider now these values here, and I'll just pop these on, let's go for that colour. We can say that the coordinate here of A is going to be x1, and the coordinate here of A for y is going to be y1. Here for B, we've got x2 and we've got y2. All we're doing is looking at the difference between the x-coordinate squared and then the difference between the y-coordinate squared. And that, of course, is going to give us the hypotenuse squared. So if we look at this now, again, substituting in these values, we can say now that d squared is going to be x2. Well, x2 is 6, x1 is 2, so it's just 6 minus 2, which we need to square. And then it's the change in the y-coordinates, which is going to be y2, which is 4, and y1, which is 1, so it's going to be 4 minus 1, which we need to square. So the distance squared, or AB squared, is going to be 4 squared plus 3 squared. Now, look where we are. AB squared is 4 squared plus 3 squared, d squared is 4 squared plus 3 squared, so we can see that's a nice, easy way to do it. So the advantage of the formula here is that we can find more challenging examples when we can't draw a right angle triangle. So if I wanted to draw the line segment between R and S, that's going to go just here, we could find now the length of this. What we need to just be careful of is not leaving our answer as SR or RS squared or D squared. We need to take the square root. It's an error students often make. So let's go ahead. What we can say then is RS squared is going to be equal to, we're going to do the change in x, or x2 minus x1, which is going to be now 3.5, and then we're going to subtract from that now 0.75. We need to square that, plus now the change in y. Because I started with 3.5, I need to start with the negative 1.5. We can't swap the x's, x1s and x2s and y1s and y2s round. We need to stay consistent. We can, of course, do x1 minus x2 all squared as long as we do y1 minus y2 all squared. We can't muddle them around. Here we need to be careful. We've got negative 1.5. Then we're going to subtract from this now the negative 3.75. So all I'm going to do is put this in a calculator and find the answer. So this gives me RS squared. So if I want to find RS, I will simply take the square root, as I've done here. So I'm going to type it in my calculator. So what we'll get is 3.5. We will subtract from that 0.75. And again, this works nicely with fractions. We're going to square that, and then we will add to that now the quantity negative 1.5, and we'll subtract from that now negative 3.75, and we need to square that. So all I've done is said now we've got x2 minus x1 all squared plus y2 minus y1 all squared. It's just Pythagoras. That's going to give us the square root of 202 over 4. We call that answer an exact answer. If you ask for an exact answer, don't hit the S to D button, which is the decimal equivalent. This is in third form and it is exact. So just leave it like so and we're done. Of course, if you wanted to see this one in action, this is straightforward and we'll quickly do that. So on a calculator now, what we would do, well, one of the things we could do is the square root of 3, and then we've got now, so 3 subtract now the negative 5, and we would square that. Then we're going to add to that now negative 3, so negative, let's put in a negative, let's want that one, don't we? Negative 3, subtract the 3, and we will square that. This is going to give us 10. So if we do that, there we go. We could have done it the other way around. We could have done negative 5 minus 3. It really doesn't matter. And just to show you that, what we could have done is gone the other way. As long as I'm consistent, so it's negative 5 subtract the 3, and we need to square that. And then we're going to add to that now 3, subtract now the negative 3, and we will square that. And let's just put the second bracket in, and this will give us 10 as well. So you can see you can do it either way around as long as you're consistent. So nice and straightforward, and that is the distance formula, or the length of a line segment, or the distance between 2 points. So let's go ahead and do some of these. And we're asked in this question to find the distance between the 2 given points, leaving your answer in exact form where appropriate. So, as we were before, if it's in exact form, that means it's going to be in a surd form, or square root, and we just write down what it is. Okay, first one, we got 5, 6, so that's going to be just here, that's 5, 6. And we got 1, 3. Now, with this one, we've got integer, whole number values, so this should be very straightforward. And I can see what it's going to be already, because it's similar to the one that we had before. It's just located in a different place. So if I look at the base of the right angle triangle, and I look at the height of the right angle triangle, I've got our special triangle again, and this is a 3, 4, 5, so that's a 4, that's a 3, so this length right here, using Pythagoras, will be 5. So we can just say it's going to be 5. If you weren't comfortable doing that and you preferred the formula, we could simply say now that d squared is going to be equal to 5 minus 1, all squared, plus 6 minus 3, all squared. And that's going to give us now on here 16, so that's going to be 4 squared. If we'll just write 16, doesn't matter. 3 squared, that's going to give us 16 plus 9. That gives us 25. Therefore, we can say now d is going to be equal to 5, as it's the positive square root of 25. So exactly the same. Okay, let's look at the next one. We got 4, 1 and 10, 9. If you're really quick, you can do this without trying, because we can look at the difference in the x-coordinates. So let's say now that d squared is the difference in the x-coordinates. So that's going to be 10 minus the 4, which is going to give 6. So 10 minus 4, all squared. Plus now the change in the y-coordinates, which is going to be 9 minus 1, all squared. So that's going to give me 6 squared plus 8 squared. That's going to give me now 36 plus 64. That's going to give me 100. Therefore, the square root is going to give me positive 10. So the distance between those 2 points is 10. Don't say it's 100. If you think of a triangle with one side length of 8, one side length of 6, there's no way that hypotenuse could ever be 100. Even if it was a straight line, it would only get up to 14. So just be careful. And let's say you could draw it, you could sub it into this, or you could just say this is x1, y1, x2, y2, put it into the formula. I do prefer to see this more holistically as Pythagoras, just the way I prefer it. Okay, -1, -4, and the origin. Well, the origin is just here, so that is going to be 0, 0. Origin just 0, 0. -1, -4 is just down here. So all I'm going to do is draw the hypotenuse of the right angle triangle, like so, to there. Then I'm going to draw the longer side of the 2 short sides, if that makes sense. So that's a bit wonky, doesn't matter, we can put that in again. So that is one shorter side, that is the other. We can see the side lengths right here. So all I'm going to do is put that this here is going to be 1, this is going to be 4. So we can say now, and I'll call this O, the origin, and this point P. We're not told that, I've just decided that. So OP squared is going to be equal to 1 squared plus 4 squared, which is going to give us 1 plus 16, which is going to give us 17. Therefore, and there's the therefore symbol, OP will be equal to the positive square root of 17. Root 17 is an exact value. It's what we call a surd, and we would leave it like that. No requirement to write 4 point whatever, it's just left in exact form. Again, you could have used the formula on this if you prefer, and you could have simply said now that d squared, or OP squared, is going to be, and we can do this either way round, we could have negative 1 minus 0, all squared, plus negative 4 minus 0, all squared. Well, that's going to give us now 1 squared. Remember, when we square a negative, it's the same as squaring a negative is the same as squaring a positive. Perhaps I should, suppose it's a bit slack of me just to write that. I can write that as 1, and then I can write this as plus negative 4 squared is 16, so d squared is 17. Therefore, we can say now that d is the positive square root of 17. Again, you could have turned those around. You could have done 0, subtract negative 1, all squared, plus 0, subtract negative 4, all squared. Exactly as we would have got. Okay, hopefully by now this is getting to be quite straightforward and quite routine. I'll draw the next one, negative 1, which is there, 1, 1, which is just there. So we've got a little right angle triangle that we could do. Let's just go ahead and draw that. We want that distance right there. Well, we can see we've got a base of 2 and a height of 2, and that should be nice and straightforward to calculate. So we've got 2, 2, and this length right here is going to be the square root of 2 squared plus 2 squared, which gives me the square root of 8. If you've done any work with surds, you'll know that this is going to be 2 root 2. If not, just stick it in a calculator. So what you'll get if you pop this in, if you put in 2 squared plus 2 squared, it will just give you 2 root 2. If you put in the root of 8, it will give you 2 root 2, as the calculator simplifies it for you. If you haven't done surds, not a problem. That is the exact value. If you want some idea of a decimal answer, that's going to give us about 2.83. 2.8, yeah, it's not bad. 2.828, not too horrendous. But do make sure that that length is longer than both of the shorter sides, as it's the hypotenuse of a right angle triangle. Okay, we'll do another one. Let's look at this one. Right, this one, slightly interesting, and again, if you think of this graphically, it'll save you a lot of time. If we pick the first point, which is 5, 3, and the second point, which will be just here, which is going to be 5, 7, we go up 1, up 2, up 3, up 4. The distance between them is 4, because they have the same x-coordinate. So if one of the sets of coordinates are the same, they're on a straight line through one of the points either on the x-axis or y-axis. So they're on a line, x is equal to some value if it's the first number the same. If the second number is the same, it's y is equal to some value. So it's literally the difference between the y coordinates in this case. Now let's say you did not spot that. Let's go for d squared is going to be x2 minus x1 all squared, the difference in the x coordinates, plus y2 minus y1 all squared. So the distance squared is going to be equal to, well, 5 minus 5, that's the change in the x coordinates all squared. And then you can do this either way around. You can do 7 minus 3 or 3 minus 7, as these two numbers are the same. I'm just going to do 3 minus 7, purely based on the fact that what we'll have now is that d squared is going to be equal to 0 squared plus now negative 4 squared. Well, that's going to give us that d squared is equal to 0 plus negative 4 squared, which is 16. So therefore, we can say d is equal to a positive square root of 16, which is 4. Again, if you'd done it the other way around, 7 minus 3, it would have given you 4. 4 squared is the same as negative 4 squared, and that is why I chose that one. So there we go. So these are nice straightforward questions working forwards. What we're going to do to finish off with is try a slightly more challenging question and see how we get on with it. So it says, given the distance between the points p, 3 and 4, 1 is 2 root 5, find the possible values of p. Okay, all we're going to do is get the distance formula. we know that d squared is going to be equal to the change in the x coordinates x2 minus x1 all squared plus the change in the y coordinates y2 minus y1 all squared. If you don't like memorising that formula, don't. Just think of the distance between the x's, the distance between the y's, and that's nice and straightforward. So let's go ahead and work this out. So this time we're given the distance and we're simply going to substitute that into the left hand side of this equation. So we got 2 root 5, which we're going to square, and that's going to be equal to the change in the x coordinates. You've got a choice here, p minus 4 or 4 minus p. I'm going to do p minus 4 all squared, purely based on the fact that it makes my expansion easier. This is nicer than 4 minus p for me. As I've chosen p to be my first value, what I need to do here is choose 3 to be, and it's going to be 3 minus 1 squared. So if I've chosen p minus 4, I've got to do 3 minus 1. If we square this quantity, this is going to give me 20. Again, you can check that on a calculator if you're not comfortable with that. If we did now 2 lots of the root of 5 and we square that, that's going to give us the 20. At this stage, I could go ahead and expand these brackets. I'm not going to. I'm just going to write it as p minus 4 all squared. This right here, 3 minus 1 is 2, 2 squared is 4. I could rewrite this now as p minus 4 all squared is equal to 16. If you want, you can expand it out. The reason I'm not expanding out is I can simply square root both sides of this equation to have p minus 4 is equal to plus or minus the square root of 16, which is going to be 4. That's going to give me 2 solutions. So if p, let's just put this in, p is going to be equal to, adding the 4 to both sides, plus or minus 4. So p will be equal to 0 or p will be equal to 8. So all I've done is solve that. Now at this stage, if you didn't like this particular approach, what you could have done is expanded this out. We would have had p squared minus 4p, which is minus 8p, plus 16 is equal to 16. The 16s will cancel. We'll have p squared minus 8p is equal to 0. Factoring p minus 8 is equal to 0. So p would be equal to 8 or p would be equal to 0. So whichever way round you'd like to solve that quadratic, that's perfectly fine. If we look at the wording of a question, the possible values, that would suggest that it's going to be at least a quadratic equation. If I had a linear, we would have only found 1. So a linear wouldn't be a squared term. So that's the advantage that we have now of setting up this and doing it. So what does this look like then, now that we've found those values of p? Well, what it's simply saying is that we've got 2 points. So let's start with this point 4, 1. Let's say 4, 1 is here, and we'll put that there. So 4, 1 is just there. If p is 0, we've got now this point just here, and that is going to be 0, 3. And if p is 8, that is going to be just here, and that is going to give me now 8, 3. So all it's saying now is that the length, if we do this, it'll just create an isosceles triangle. That length is the same as that length. So we can put that on if you wanted to connect it up as a triangle. You certainly don't have to. But that's what we get. We get this isosceles triangle, and we can say that these 2 lengths are the same. So all I did was substitute it into the distance formula, which gave me a quadratic in p, solved for p, and found those 2 possible values. If you're unsure, check your answer, sub it back in, make sure it works. But that looks good to me. The diagram looks nice and clear, and we've answered that question. So there we go. That is the distance formula, or the length of line segment, or the distance between 2 points. Just remember, it's no more and no less than Pythagoras Theorem.